Good morning, ma'am. Myself N. Bharat. I am from second ECE in probability and complex variable. Today my topic is about problem solving about boundary of the region. Introduction to boundary of the region in probability. Boundary regions often represent critical thresholds where outcome change specifically in probabilistic models. Understanding these boundaries is crucial for accurately modeling real world phenomena and making informed decisions. Techniques such as simulations and analytical methods can be employed to explore and visualize the boundary region effectively. Complex variables and their boundary conditions. In complex analysis, boundary conditions play a fundamental role in determining the behavior of analytic functions. The interplay between boundary regions and singularities can lead to varied results in the evolution of integral and series. Applying Cauchy's integral theorem and reducing theorem helps in solving problems related to boundary regions in complex variables. And my question is, evaluate closed integral y square plus 2x into dx plus x square minus 2y into dy, where c is the boundary of the region, by y equals to x square and x equals to y square. It gives in a given problem y equals to x square and x equals to y square. It means these both are parabolas. Given that closed integral y square plus 2x into dx equals to plus x square minus 2xy into dy. Given boundary regions are y equals to x square and x equals to y square. Consider that y equals to x square is first equation and x equals to y square is second equation. Then point of the intersection. We know that y equals to x square is a parabola which is symmetric to the x-axis, and y square equals to x is also a parabola and which is symmetric about y-axis, and both are meet at the origin and the point P. Origin coordinates are 0, 0 and P coordinates are 1, 1. The given region intersection points are 0, 0 and 1, 1 by the given graph. The positive direction in traversing C as shown in the figure along y equals to x square. The line integral is y equals to x square. By differentiating on both sides, we get that the differentiation of y is dy and x square is 2x into dx. Given that, now problem, closed integral y square plus 2x into dx plus x square minus 2y into dy. The boundaries we know that from the given graph 0 to 1, then that equals to integral 0 to 1 x power 4 plus 2x cube into dx plus x square minus 2x cube in 2x dx. By substituting this y equals to x square and dy equals to 2x dx in the above equation, we get that integral 0 to 1 x power 4 plus 2x cube into dx plus x square minus 2x cube into 2x dx. Then by multiplying 2x with the x square minus 2x gives the 2x cube minus 4x power 4, that equals to integral 0 to 1. By adding both of these, minus 3x power 4 plus 4x cube into dx, that equals to minus 3 is a constant, so it's kept outside the integral. Then minus 3 integral 0 to 1 x power 4 into dx plus 4 is also a constant, then kept it out of the integral. Integral 0 to 1 x cube into dx. We know that the integration of x power 4 is into dx equals to x power 5 by 5, and integral x cube into dx equals to x power 4 by 4. that gives that minus 3 into x power 5 by 5 the boundary is 0 to 1, and 4 into x power 4 by 4 into boundaries are 0 to 1. Here 4 and these 4 also cancelled. Now by applying the limits in the boundaries, in the replacing of x, minus 3 into 1 by 5 minus 0, because upper limit minus limit lower limit 1 by 5 minus 0, and x power 4 means 1 power 4 it is equals to 1, so 1 minus 0, minus 3 by 5 plus 1 that equals to, the LCM is 5, therefore minus 3 plus 5 by 2 that equals to 2 by 3. Consider these 2 by 5 as equation number 3. Above the figure, along y equals to root x, the line integral is y equals to root x. Along x equals to y square, the line integral is of x equals to y square, differentiating with respect to x. Dx equals to 2y dy, y dy equals to dx 2, dy equals to dx by 2y, dx equals to dx minus root x. Given that closed integral y square plus 2x into dx plus x square minus 2y into dy, we know that the limits are 1 to 0. Now the cycle is reversing from p to 0, p to o. Therefore p point is 1 and o coordinate is 0. Therefore closed integral 1 to 0 x plus, substituting these equations in the above equation, we get that x plus 2x into x to the power of 1 by 2 into dx, x square minus 2x into x to the power of 1 by 2 dx by 2 root x. On solving, we get integral minus 1 to 0 x plus 2x to the power of 3 by 2 into dx plus 1 by 2 into x to the power of 3 by 2 minus 2x into dx. Again we solving, that equals to integral 1 to 0 x plus 2x to the power of 3 by 2 plus 3x by 2 by 2 minus x. Therefore integral 1 to 0 x dx plus 2 is a constant, integral 1 to 0 x power of 3 by 2 dx plus 1 by 2 is also a constant, integral 1 to 0 x to the power of 3 by 2, that minus integral 1 to x dx. Solving this, we get 2 into x to the power of 5 by 2 by 5 by 2, the limits are 1 to 0, and 1 by 2 into x to the power of 5 by 2 by 5 by 2, limits 1 to 0. By keeping the boundary inside the equation, we get 2 into 0 minus 1 by 5 by 2 plus 1 into 0 minus 1 by 5 by 2, that equals to minus 2 by 5 by 2 minus 1 by 2, that equals to 1 by 4 minus 1 by 5, and the PP is complete.